Good afternoon, everyone, again. Thank you for coming to my second talk. I'm Xiao Chen. This work was done with Yurong, Puneet, and Kyuhang at HP Labs. I also want to thank my advisor, Ramesh Govina, for his generous support for this work. So, e-commerce is very popular today. However, most of today's purchases are still made in brick-and-mortar stores. This looks amazing, but it is a fact. However, I think everyone believes that the online shopping will surpass the physical shopping one day because we have so many benefits like targeted ads, customer reviews, and online coupons. In the meantime, what do we get from those physical shops? So the customer gets overwhelmed in front of the rack, don't know about the items because they don't have the ads, they don't know the reviews. On the other side, the store doesn't know the customer's shopping interest, so they cannot provide specialized, customized shopping experience. The online shopping relies on two things. First, the customer identity. Second, the shopping interest. These two types of data can be retrieved with user's web browser. With this data available, all the following features will be possible. If we want to bring all the online features to offline, we also need to get those two types of data. However, for a physical store, how can we do this? The answer is we need a system that identifies the user and tracks her movement in the store. For the identification part, the system should recognize each customer in the store. The customer ID can either be the people's real ID or the device ID. For tracking, the system should track each customer accurately, both in one region and across a store. When we get the customer's trajectory, we can understand which racks or products he is interested in. Currently, there are two types of solutions. The first category is based on computer vision. This system uses cameras to capture the shopper's face or body features for identification and tracking their movement. We already have some fancy demos like Amazon Go. However, for such solutions, they have two problems. First, the vision accuracy highly depends on the image quality and camera coverage, for which many stores may not have qualified hardware. And also, collecting people's faces may trigger their privacy concerns. Another solution leverages sensor on users' smartphones. For example, Facebook and Twitter use users' GPS location to infer which store they are in, and Walmart uses RFID receivers on shopping racks to sense the approaching customers. These sensor-based solutions can easily get device ID for identification. However, due to the noisy signals in hardware, they might not be good for fine-grained tracking in the store, and some of them may drain the battery very fast. In summary, vision techniques are good in accurate tracking, but not identification. On the other side, the sensors are better for identification, but not tracking. Can we bring these two benefits together? So we designed TAR to do this. Here we assume that each customer will carry their smartphone during their stay in the store. There are three challenges. First, how can we associate the same person's visual track and her sensor data? Second, there are many challenging cases for people tracking, which may cause many failures. Third, it is challenging to calibrate all nodes in the store and make their results consistent. First, let me share some key insights for our design. We find Bluetooth Low Energy is a good choice for the sensing part. BLE has very little overhead to the energy or computation. A coin battery can support the device for several years. The BLE protocol is available in any smart devices, so we can easily turn a device into a BLE beacon. The next insight is that we can use the received BLE signal strengths to estimate the distance between two devices. We call this BLE proximity. For detail, please read our paper. For vision, we can estimate the actual distance between the customer and the camera by analyzing the video. As this figure shows, if we know the parameters of a camera, we can create a one-to-one mapping between a point on the floor and its corresponding pixel in the image. This mapping is called camera homography. Then we can use the people's foot position as her standing point and turn the pixel position to infer her actual distance to the camera. Now we have BLE proximity and visual distance that both are similar to the actual distance. So we no longer need the actual distance anymore. For BLE, we can use the UUID for identification, and from the vision, we can get the working trace. So problem solved. Then we created the basic logic of TAR. It extracts both data and uses the trace matching metric to associate two traces for the same person. Here is an example from the surveillance camera. With TAR, we can track her movement associated with her device ID. With this information, we can provide similar services as online shopping. Now let's take a look at how TAR matches the traces. In the camera, we capture one person with his vision trace and BLE proximity trace. At the same time, we have another people here. For each vision BLE trace pair, we use dynamic time wrapping to compute the dissimilarity between two patterns. DTW is a dynamic programming-based metric that measures the distance between two time series, and it is more robust to noises than other metrics like Euclidean distance or cosine distance. For all the vision BLE pairs, we compute their pattern distance and form into a matrix. Each cell represents a pair's distance. Then we apply a transform function to convert the distance values to matching confidence. Generally, the lower pattern distance it is, the higher confidence we have to believe that two traces belong to the same person. Since each person in the camera is continuously generating new traces, TAR updates its confidence matrix using the sliding window scheme. Now it computes the confidence for traces inside the window. At the right bottom, we can see the change of two confidence scores. As the traces become longer, TAR accumulates the confidence for current window to existing matrix. We can see the correct matching's confidence becomes higher. The longer trace we have, the higher confidence we compute for the right pairs. At each second, TAR uses Hungarian algorithm to find the best matching globally. Now, I will show how TAR handles corner cases in tracking. There are two important things. The first, the tracking should be correct. And second, the traces should be long enough so we can get high matching confidence. However, the vision tracking sometimes fails because of people across each other, occlusion, etc. The trace length is also not guaranteed, since one person may appear in a video only for 1 to 2 seconds. TAR's vision tracking is based on the state-of-the-art online tracking algorithm called DeepSort. It uses both people's visual feature and trajectory for accurate tracking. We add 3 optimizations to improve its performance. First, we added a kinematic filter that keeps tracking each person when they cross each other. This helps reducing ID switch, which means the two people's tracking IDs are switched when they cross each other. Second, we find the vision-based tracking easily fail when people overlap. This is because the overlapped people, their detection bounding boxes will also cover other people, which makes it hard to differentiate using visual feature. So TAR just tracks the overlapping people as a group to avoid feature collision. Third, we implement our own deep neural network model for people feature extraction and train it with 2 large pedestrian datasets. Our model can generate a more representative feature than the default DeepSort. For the broken trace, let's see an example. First, this guy is successfully identified as IDA, then his track is occluded. After a few seconds, his track appears again, but this time it's too short to be confidently identified. The red dotted line shows his walking trace during occlusion. Now we have trace 1 identified and trace 2 unknown. TAR will generate a trace from track 1 to trace 2 and combine them into a new track. Then it tests if the new trace can also be identified as IDA with high confidence. If yes, this means the unknown trace 2 is an extension of trace 1. Otherwise, we should try something else. In the word, TAR merges short traces to longer one to increase the matching confidence. The third question is how to calibrate all the cameras. We also face two problems. First, multiple cameras may match different traces to the same ID at the same time. And second, for each camera, since its sensing range is just a small portion of BLE sensor, which means many sensed BLE IDs are outside of the video, and they will bring a lot of uncertainty to the BLE matching process. We can use the same solution for these two problems, called ID filtering, which removes invalid candidate BLE IDs. TAR extracts the camera topology into a graph, and it uses the cross-camera dependency to filter out BLE IDs. For example, node A and node B cannot have the same ID at the same time, and node C cannot assign the ID for the person who comes from the node A before B and D, because they have spatial dependency. We tested TAR in two environments, the office and the retail store. We recruited 20 participants to install our BLE library on their phones, and they do random walking in those areas. The test data recorded up to 27 people being simultaneously tracked, because there are many people that are not our volunteers, and they don't have device. Each node in TAR runs on one GPU machine with one camera and one BLE receiver. The results in the two environments shows that TAR has much higher identity tracking accuracy than existing state-of-the-art vision-based solution. This solution comes from Duke MTMC. Here, the vision solution leverages deep neural network to generate people's body feature and uses that feature for both identification and tracking. We analyzed all the error results. About half of TAR's errors come from wrong BLE vision matching, and the rest are due to wrong tracking trace inside one camera. In the vision solution, only about 20% of errors are due to tracking. All the rest are caused by identification, which means the system classifies one person's feature to be another person's. Such vision failures comes from many aspects, like bad image quality, partial occlusion, and similar figures. Therefore, we can see that vision is not reliable by itself. We randomly turned on some nodes in TAR to test its robustness. The result shows the system is robust to failures because each node runs BLE vision matching by itself, and the only loss is the benefit from the cross-camera ID filtering. In conclusion, the vision-only people identification and tracking are not reliable. TAR combines BLE and vision for accurate people tracking and identification. We have multiple optimizations to handle challenges like occlusion, short traces, and ID collisions. In the test, we show that TAR outperforms the state-of-the-art vision solutions. So that's all for my talk. I'm good, ready for questions. Thank you.